I'm coming from. I'm at Texas A&M University in College Station, Texas. So if you think of all your what cities in Texas you do know of, I'm not from any of them. Houston is off over here. Dallas is up here. Austin, where the University of Texas is, over there. So College Station is right in the middle of nowhere, or in the center of everything, depending on how you want to phrase it. Our Texas A&M Supernova group is here with Professors Nicholas Suntsev, Lifan Wang, Kevin Krishunas, just recently retired, but is still research-wise active with our group. Shuvo is a postdoc working with me on ultraviolet things. And then our graduate students, Yaswant and Michaelin, work primarily with me using SWIFT data on type 1As and core collapse supernovae, respectively. We'll get into that. And then the other graduate students, Lauren, Jawen, and Jisa, and then Divya just joined us. So that's kind of the group that I'm coming from. The other thing that I really need to introduce is the SWIFT, originally called the Gamma Ray Burst Observatory, because its original mission was to study gamma ray bursts. So as Luis mentioned, it was launched in 2004, which was my third month as a graduate student. So I got there just in time, which was a great way to get in right in on the beginning. It has 3 co-aligned instruments. The Burst Alert Telescope covers about 1/6 of the sky in hard X-rays, soft gamma rays, in order to detect gamma ray bursts, which I won't go into a lot of detail, but SWIFT was designed to detect these gamma ray bursts and then immediately slew narrow field instruments in order to observe what's called the afterglow, basically the leftover heating of the environment around the gamma ray burst, which can glow in the X-rays and optical and infrared and radio and everything else. But the idea was to rapidly point, and when we're talking about a minute. So within a minute, it will detect and then repoint SWIFT to then observe the X-rays and gamma rays. So then the 2 co-line instruments are the 2 narrow field instruments that are co-aligned to the center of the Burst Alert Telescope is the X-ray telescope, 0.2 to 10 keV. And what I will be focusing on in this talk and in my research is the ultraviolet optical telescope. So because gamma ray bursts are unpredictable, both in where they're going to happen, when they happen, and how they behave, SWIFT was designed to be very flexible in how it would be able to observe these gamma ray bursts. So it can autonomously repoint itself. It figures out, is it safe to observe? How long will I be able to observe before the Earth gets too close? Is the sun out of the way? Are bright stars out of the way in terms of the narrow field instruments? So it can repoint the ultraviolet X-ray capabilities autonomously. It also has an upload mode where the scientists and engineers on the ground can upload a target to just say, okay, pretend this was a gamma ray burst, look at this as soon as you can, and it'll figure out, okay, can I look at it right now? And it will override the existing observing plan to observe that high priority target. The schedules of what it is observing are revised on a daily basis during the week and start that night. So if I ignore time zones and we're on a Thursday afternoon, they would have, well, okay, we're coming up on a weekend. So no, wait, we're on a Friday. Okay, I'm completely lost as to which what day of the week it is. So on a Friday coming up on a weekend, they'll actually have they will just now be uploading a schedule of what's going to go on Friday, Saturday, Sunday. And then Monday they'll come in and say, okay, we've made a plan for Tuesday. Is that still what we want to do? And Monday morning they can still revise what's going to be observed on Tuesday. So it has this short-term scheduling that allows them to change things flexibly. And the data, as soon as it's downloaded to NASA and then processed, it's pushed to a web archive. And so usually within 3 hours of an observation, you can have data available to look at and be able to evaluate, okay, if it's a gamma ray burst, okay, have we found the source? Which filters is it detected in to get maybe a photometric redshift? And here's the position that we can get out to other observatories, because getting the data out fast and notifying other people is really important for gamma ray bursts to get multi-wavelength follow-up. Now, all of those same characteristics are also super helpful for supernova observations. So when a new supernova is detected, I receive an email about it. I check, okay, is this the type of thing we want to look at with Swift? I can submit a TOO request, and within, so I'm usually requesting observations within 24 hours. I usually get a response within a few hours, but they can respond as quickly as within, I've had Swift observations happen within the hour of me notifying them that there was an object that we wanted to observe. So all of these useful characteristics that were built in and the flexibility built into Swift have made it a super observatory for supernovae. Now, since I'll be focusing on the ultraviolet optical telescope, just to let you know the wavelength range of these filters and the names, which I don't expect you to memorize, but they will be showing up in the plots. So we start with some overlap in the optical with a V band and a B band that are very similar to ground-based. Our ultraviolet U band is a little bit broader than what ground-based telescopes use, and we don't have the pesky atmosphere in the way, so we go all the way down to 3,000 angstroms. And then we have 3 unique space UV filters, UVW1, and then in what I would call the mid-ultraviolet, we have the UVM2 filter, which is the red curve, and then a UVW2 filter. Now, for a lot of the plots that I'll talk about, many of them will focus on the UVM2 filter. They're in red. It has a sharper cutoff in the ultraviolet, a sharper cutoff on the optical side, so that there's not as much optical leak, you could say. And so that's sort of the filter that I'll use most often. Although we get observations in all 6 filters, so we can measure colors and we can do an SED across different bands. But in terms of some of the science that I'll show, UVM2 I find to be the most useful. Okay, so to compare what was done pre-Swift, so the International Ultraviolet Explorer obtained low resolution and usually kind of low signal to noise UV spectra of about 2 dozen supernovae. So in the top right panel, those are taking spectrophotometry from a filter similar to one of Swift's. Those were what we've seen. Typically, it observed the brightest supernova of each year. There also weren't as many supernovae detected each year back then, but the brightest supernova, or up to 3, is what they observed. And then the plot on the bottom left, it had 10 years of experience when supernova 1987A exploded, so it was able to observe that with crazy amounts of data to observe. I mean, you see in the top left, in the first few days after explosion, that it dropped by 7 magnitudes. So that's a lot. We'll talk a little bit more about shock breakouts, but basically that's the explosion first coming out. It's super hot, but as the supernova expands and cools, it cools off quickly. The UV flux drops dramatically, and then you have that next bump there is radioactively powered, and then I forget what's going on at later times that we don't usually get to observe with supernovae, and 87A was kind of unique as well. Okay, but it also it gives you a flavor for the amount, the quantity of the data and what we knew in the ultraviolet before Swift. Okay, but just to cover roughly the supernova classifications that were in this plot. So color coded, there were several type 2s. Those are in blue. They are really blue. They have more UV flux. In green is a stripped envelope core collapse supernova, a type 1b, and then in red are the type 1a supernovae. So in our supernova classification scheme, the type 2 supernovae are the ones with hydrogen in them. They're the red giant explosions. Now, if there's no hydrogen because that hydrogen has been blown off and there's helium, then that's what we call a type 1b supernova. If it's even more massive and the helium's gotten blown off as well, then that winds up being what we call a 1c supernova. And then a completely different kind of explosion, but which based on the observational classification, not having hydrogen, but having strong silicon, are the type 1As, the white dwarf explosions that we use for cosmology that I'm assuming you've heard a lot more about. We'll talk about these a little bit later. But I wanted to mention the supernova classification here up front, because one of the things that Neil Garrels, who was the principal investigator of Swift before he passed away a few years ago, what he commissioned me basically as a first-year graduate student when I showed up on Swift, interested in supernovae and gamma ray bursts. This was kind of thrown at me unexpectedly that Swift was originally supposed to study only gamma ray bursts for the first couple of years, but then they were looking to broaden, and a supernova came along, and my advisor knew I was interested in supernovae as well. And he originally had said, okay, well, you've got 2 years to get your classes done, and then we'll talk about doing supernovae. But still within my first year as a grad student, I was told, okay, are you ready to do supernovae? And so I started leading the Swift supernova team from that point. And Neil Garrels asked me to form a team and to help pick the best 1 or 2 supernovae each year to observe with Swift. So that was kind of our commission. And so the goal that I set as a grad student, knowing, okay, well, there's these different supernova types. Let's kind of, if we were to map out, have one of each type and figure out what its UV characteristics are in the Swift bands, that would probably be a good broad goal and something doable with a few supernovae per year. Now, in terms of the supernova classifications, as I got to know and understand the literature better, and then as supernova scientists started finding more supernovae and finding more characteristics of them that made different types unique, they just started sort of adding to this classification scheme. There's more and more and more types to observe. And so trying to keep up with everything, but I think that we have covered most of these new classes. One of the most recent ones, a type 1CN, it's a very kind of peculiar supernova. When it was first announced at a conference, hey, we think we've discovered the so just to kind of step in here a little bit. Okay, so a type 1b supernova doesn't have hydrogen, but it has helium. If it has narrow helium lines, which is a signature that it's interacting with slow-moving material, so slow-moving helium, they called it a 1BN. And then another decade later, they found one that didn't have helium, but it had narrow oxygen and carbon lines, and they called that a 1CN. And when Avishai Gallium said, hey, we've discovered one of these, my first thought was, oh no, now we're going to have to try to find one of these super rare things so we can observe it with Swift. But as part of the ZTF team, his team had already triggered Swift on it, and they already had observations. So that was good. So until you guys discover a new weirdo, I think we're kind of complete. In terms of picking the best 1 or 2 supernovae per year, I feel like we've done pretty well with that. But you don't necessarily know which the best supernova is when it goes off. But we've done that by observing quite a few more than one or two per year. So I like to describe this as the explosion in ultraviolet observations. You have a few 1 or 2 supernovae per year with IUE and some other instruments, the Hubble Space Telescope. And then when SWIFT launched, then immediately we started observing a lot more. And as we learned how to better observe supernovae, and we learned this, better understood the science case for observing supernovae in the ultraviolet, then we both proposed more, and we were allowed to, okay, yes, this is something that the SWIFT wants to do, and we'll observe lots of supernovae. So just a reminder, this is what IUE had observed, and this is kind of what the sample that I was originally hoping for in terms of a good example of each supernova type. The x-axis is days since explosion. So this is the time evolution of, on the top panel is the mid-ultraviolet luminosity in our UV-M2 filter. And on the bottom is the UV-M2 minus V color. So you can think of it as a filter ratio between the ultraviolet and optical flux, where the very blue objects are in the bottom left corner. So these are supernovae when they first explode and they're really hot and they cool down. So that corresponds to the top plot where a lot of the supernovae are fading at early times. Meanwhile, for example, the one in red in both plots, it's seen most easily here in the top plot, a type 1a supernova that is mostly driven by the release of energy from radioactive nickel. You have the effect of the supernova expanding, getting bigger, and that energy being able to be released, as well as then the half-life of nickel. So you wind up with this rise for 2 weeks and then a decay. And meanwhile, that type is very, very red, buried here in a UVM2 minus V color around 3 or 4. Okay, so this kind of gives you an idea of the different supernova types, the great variety that we see and how they behave in terms of their colors and their luminosities. And there's a lot more that could be said just about this plot, but this is kind of a summary of lots of different objects. But now we've observed hundreds, probably nearly 1,000 or more supernovae that we've now observed. This is a plot on the same type of scale with the UV luminosity on the top and the UVM2 minus V colors on the bottom. We've now got, instead of a single example of each type, we've got dozens of the major supernova classes. And now we're working towards having multiples of the even rarer subclasses. So we can get an idea of not just how do different classes compare with each other, but within the same class of supernova, how much diversity is there. I should say, if anybody has questions along the way, feel free to raise your hand and ask, or if I've skipped past something and start using an acronym that I haven't defined already, just wave your hand and let me clarify. So one of the major projects that I've been working on is the SWIFT Optical Ultraviolet Supernova Archive. That's basically making all of these light curves available. Because I've had the experience working on the SWIFT UVOT team and being a supernova person, so I understand some of the ways that we would like the data analyzed and some of the peculiarities in the data. I've sort of been taking it upon myself to reduce the data for everybody else or anyone that wants me to just do it for them. And so my SUSE archive is sort of a compilation of the data, which is the raw data is publicly available. Anybody can get it and deal with it themselves if they want. But if you want the bad frames already pulled out. If you want everything organized by supernova, organized by filter, then I make those available, as well as my photometry products and light curves on and then I have the easiest downloadable data on a Swift Supernova website, where you can also look at pretty pictures and things. And so that's been one of my projects. Okay, are there any questions before I shift more to the science? Any questions about Swift? Okay. Yes. So the question was, why am I plot of supernovae per year? Why did they drop off at the end? This just happened to be when I made this particular plot, was at the beginning of 2019. We'd only started our supernovae for the year. But there's also another aspect in that is with these great numbers of supernovae that are being observed and being proposed by different groups. I'm no longer able to keep up with them all in real time. As a graduate student, when we were first doing a couple per year, I would every day, basically my job as a graduate student, every day I would come in and say, here's the data we got yesterday on this supernova. We still detect it. We should observe it again in 2 days. Please put it on the schedule. And so with 1 or 2 supernovae going on at a time, that was kind of manageable. I had separate email folders for each individual supernova, but kind of as kind of a data scaling effect. Okay, I've had to figure out how to deal with more and more supernovae, and to the point now where, you know, there's going to be a lot of supernovae that are going on that I'm not personally following. Once it hits the archive, well, again, part of the scaling effect. Now I'm recruiting undergrad students to help run my pipeline, and okay, here's you 100 supernovae. Go work on those. So that's a good observation of what's going on there. A good way to explain some of the grad student effort that I was putting in at the time. Any other questions? All right, so the science, I'll sort of follow a little bit by supernova type, starting with the type 1As, the thermonuclear white dwarf explosions, because they have a similar, or at least seem to have a similar mass at the time of explosion, a similar explosion energy. These are the ones that we use as these type 1A supernovae are what we use as standard candles to measure distances in cosmology. Now, the way that is done is by using them as standard candles, calibrating how intrinsically luminous they are, so that you can measure how bright they appear, and from that get a luminosity distance. Okay, that's at the most basic level how we use them. They're not quite all the same luminosity. So instead of standard candles, sometimes we use the awkward phrase standardizable candles. That, for example, here, the light curve shape is correlated with the luminosity in the optical. So we can improve our precision and accuracy by using the light curve shape to calibrate the luminosity. And this works in many different bands in the optical and the near infrared. However, in my thesis work was looking at the absolute magnitudes in the ultraviolet, where they are not standardizable. And so in this plot, along the x-axis, you have the light curve shape. If you start at the bottom with the V band and the B band, these are the optical bands. The grayish lines are the calibrated optical absolute magnitudes that in our Swift data, we're consistent with that and their dispersion. But then as you get, the U band is still okay, but as you get towards the top, the UVW1, it starts to show a little bit more scatter, but then the UVM2 especially, you see a jump where instead of 0.2 magnitudes of scatter that you might see in the optical. It's almost 2 magnitudes. Okay, so that was a in terms of my paper on that was supposed to originally be titled, "Are they standard candles in the UV?" And I was told that it sounded too much like a National Enquirer headline, and that if you're asking a question like that in as the title, that usually the answer is no, and the answer was no. And so one question would be, well, is it just ready? Okay, the extinction laws increase in magnitude as you head towards shorter wavelengths. They also increase in diversity. So one way that I've looked at this is in terms of the colors of the objects. So in this color plot, so these are the colors measured at the time of maximum light in the optical, or in the B band specifically. On the bottom is the B minus V color, which we often use as a proxy for reddening, if you assume that they all have the same intrinsic B minus V color. And on the left axis is our near UV W1 filter minus the V band. And these lines that you see represent reddening vectors using different kinds of extinction laws, similar to what we have in the Milky Way versus what's in the small or large Magellanic Clouds, or even if it's a circumstellar dust is causing the extinction, then that also causes a unique upturn in the UV luminosities. But here we have the observed peak colors of a sample of swift supernovae. The ones in red are ones that have HST observations of the spectra that I'll come to later. But what you see is that while a lot of the supernovae are pushed up and to the right, consistent with reddening, if you look just at the objects with low reddening, that dispersion in the near ultraviolet minus optical colors is evidence of intrinsic dispersion in the colors of these supernovae. Peter Milne has referred to these ones down here as near UV blue, while everything above sort of this cutoff line here as near UV red. Okay, so some of those originally what you would call near UV red objects are reddened blue objects, but clearly intrinsically there are intrinsically near UV blue objects and intrinsically redder objects as well. So while the prospects of using the ultraviolet as a standard candle to measure cosmology distances is not very promising, what we're trying to use the ultraviolet for as a way to understand the physics of type 1a supernovae and how much of that diversity in progenitors and conditions would affect the optical data that we can and do want to use for cosmology. Okay, here's another way to look at those objects. On the left plot on the bottom, again, that's the B minus V color. The very top plot is similar to the one that I showed you before, but colorized based on the B minus V color. So the blue objects have a blue optical color, and the redder objects are the likely reddened redder objects. So the top left panel is what you saw in the other one. Again, a possible two groups. That one of the questions is if you've got objects that are bluer or redder, is the difference because some objects have more UV luminosity, or is it because other objects have less optical luminosity? And so then the middle plot on the left, this is it's a proxy for the absolute magnitude in the UVW1 band, where we've corrected for distance but not dust. Again, because if I'm not sure which dust law to use, or what the intrinsic color is, I don't want to correct for that directly. Oh, sorry. And so when we do that, we wind up with, out of these 4 objects that were blue in the UV, 2 of them turn out to be brighter in the UV. And then 2 of the objects turn out to be at the faint end of the optical. So there's not necessarily a clear answer of what's going on, that there's an element of the UV and the optical being affected that we don't quite understand. And the other things that we're looking at in the right plot, that's again, the delta M15B is a measure of the light curve shape. And so we're trying to see how much effect that has, that we know is calibratable in the optical, but doesn't seem calibratable in the UV. Now, another thing to point out is how faint these objects are in the UV. So here, superimposed on the UVOT filters, plotted in red is the UV spectrum. When I started graduate school, this was basically the only UV spectrum of a type 1a supernova that you could use from HST. You see how dramatically the flux drops once you get into the ultraviolet. So this is caused by metal lines, iron peak elements, iron to nickel to cobalt to, lots of those lines are just have lots of transitions that occur at ultraviolet energies. And so it just absorbs a lot and then shifts the energy to longer wavelengths. So that's what we're dealing with in the UV, is that there's not a lot of flux there. And what flux we do see there seems to vary by quite a bit. So if you look at different models, so at the top, that's just a reminder of the UVOT filters. This plot, the x-axis is in wavelength, in angstroms from 1500 to 6000. You see in the bottom 2 plots, these are theoretical models. If you take a supernova model and you change in the middle panel, that's the metallicity, the amount of heavy elements. I believe in this case, they were taking everything above carbon and just scaling it compared to solar. If you change the amount of heavy elements in the supernova explosion, you can dramatically change the flux there in the UV, but meanwhile have very little changes in the optical. Or if you change the density gradient, so how quickly the material drops off, as where because the supernova is expanding, you've got material at different velocities, but how much material you have at each of those velocities, that is what we're referring to as the density. If you change that structure, then also you get a large differences in the ultraviolet and very little in the optical. So I kind of refer to this as the promise and the peril, that, hey, this sounds like lots of interesting physics that we can learn from the ultraviolet observations, because it's so sensitive to metallicity, density structure, dust reddening, as well as dust scattering, if there's material around the supernova itself, or if the supernova interacts with something, then that would cause a brightening in the UV. So there's lots of exciting stuff that we can learn from UV observations. The peril is there are lots of interesting things that affect the UV. And so all of these effects are going on at the same time. And so we're having to try to disentangle these effects in order to figure out, okay, what are the dominant effects and which are secondary, and what is the magnitude of each of them? So one of the approaches I've been working with theorists, specifically Eddie Barron and Peter Hoflich, to build better models. A lot of the current models that cover ultraviolet wavelengths were built before there were more than one UV observation to constrain them with. So we're trying to expand the set of models that we can compare with. something else I should point out is understanding the differences and the dominant effect in the UV can have an important impact on cosmology because of the origin of the UV diversity. If the UV diversity that we see is from metallicity, then that is something that would definitely change, evolve with redshift as we look at earlier explosions. And so if we can figure out, okay, how much of a difference does metallicity make? And we can measure that from our UV observations and then read off from those models how much of a difference does it make in the optical. And then you can also compare, okay, then based on the metallicity differences between now and whatever epoch you're doing your cosmology at, how much difference could there be? So it's something that we might be able to use to improve cosmology. Or if the origin is something like, comes from the asymmetry in the explosion and that you're viewing it from different angles, that affects the UV a lot more than it does the optical. But your ratio of viewing angles is not going to be different in the early universe than in the current universe. So understanding the origin of the diversity has cosmological implications. So the other approach that I've been using to try to understand these better is to go beyond the swift photometry and just looking at the colors to getting more HST observations of the ultraviolet part of the spectrum, which because they're faint, you really need HST. And so we've been adding together different types of supernovae, targeting different colors where we can look with swift. Again, this is another advantage of having such quick observations with swift, is when a new supernova is discovered, then we can observe it within a day or two with swift. We can get colors and get an idea of, okay, does this look like the supernovae we've already observed with HST? Or does this look like a uniquely UV bright object like 2016 CCJ? Or is this consistent with one of the very red objects like 2017 ERP? So these were two ones from my previous programs that I was able to trigger based on knowing what they looked like with Swift. And then here's a comparison of this very red one at the bottom on that plot compared to some brighter, very well observed supernovae, plotted both on a linear scale on top as well as a log scale on the bottom, because the UV has such a different flux scale. You need them both to really look and see what's going on. But you see how similar all of these objects are in the optical, but then how much the diversity increases in the UV. And the first look at these compared with models that were made, I think it was in Walker 2016. So based on those models, metallicity is the best match for these differences, in the sense that this UV blue object 2011 FE has a lower metallicity than 2017 ERP. Now, looking at the host galaxies themselves, the host galaxies don't have as much of a difference in metallicity as what we see here. So it may not be that the metallicity of the galaxy is a global parameter that affects these supernovae as much. So that's something we're also working to understand better.
Sorry, are you talking about the global metallicity, the entire galaxy, or just like where the supernova is from?
That particular comparison was with the global metallicity. But yes, measuring a more local metallicity could be a better proxy for the metallicity of the supernova. So that's something we're looking into, and that's something that could be interesting with the IFU observations that you guys have been doing. All right, so I'll go through this element kind of quickly. One of the interesting questions surrounding 1As is still, what are the progenitors? Or specifically, if we've got a carbon-oxygen white dwarf that's exploding, what is the nature of its companion? So in 2010, Dan Kaysen put out this relatively short paper that has inspired a lot of people to look for basically the effect of this collision, where running into a companion opens this cone of shock heated material that then gives you a viewing angle dependent excess at very early times. And this excess is strongest in the UV because it has a higher temperature, so there's more flux there. But also, this is where the very low flux from the intrinsic properties of the supernova then give you an even higher contrast. So looking at swift observations in the near UV, these darker models, well, the darker ones represent different models where you've added to the 2011 FE data, you've added a shock from either hitting a main sequence companion or a red giant. And then there's some observational data plotted on there in those symbols, where basically we can really exclude, in a model dependent way, if Dan Kayson's shock collision model is correct, we can easily exclude red giants as the companion because their luminosity adds so much extra luminosity, even to the point of maximum light in the UV, that we would be able to detect that. But pushing down requires earlier observations. And as of a few years ago, we hadn't detected anything consistent with that, including 2011 FE, where even just 2 days after explosion, it was actually not formally detected in the UV. It was so faint. Okay, but as we've looked at more supernovae, we do see there is a lot of diversity in the early rise time of supernovae, but then also a few objects such as IPTF14 ATG that seem to have a little bit of excess. Some have a tiny amount of excess that, whether it is or isn't is hard to know. As supernovae have been discovered younger, sooner after explosion, and as you get more high precision data, for example, this is with the Los Cumbres Optical Global Telescope team, where they have telescopes around the globe. They can observe an object multiple times per night. You get this exquisitely detailed data, which shows an excess compared with what you would predict. And so zoomed in at very early times. This was from the LCO press release, and they call it ultraviolet brightness, but this was with their ground-based U-band. So I would call that just their violet brightness. Because when you look in the ultraviolet, the prediction for the shock is up here, and our data is down here. And so there's now been some hand waving of, well, the Kaysen shock model is good because it really fits in the optical. This is what we're seeing, but maybe there's just more line opacity that wasn't accounted for in the models or something to kind of avoid the UV data that doesn't have the same luminosity. But on the other hand, I mentioned IPTF14 ATG, or both of these plots are from 2019 YVQ, which show a clear UV excess that fades for 4 or 5 days before then you have your radioactively powered thing. So we are seeing a few objects where something is going on there. So now we just have lots of more open questions instead of, is there a shock? Can we say something about the companion? Now we need to understand, okay, well, what are the UV excesses and what's going on when there isn't a UV excess, but there is a bump in the optical? Is it an effect that we have multiple channels or things going on? So still lots more questions that have been raised. Now I'll briefly mention that for core collapse supernovae, you expect, and we do see, a bump at early times, and that's from the shock breakout of the explosion itself. Again, it gets really hot at the beginning as the explosion reaches the surface, but then as it adiabatically expands and cools, that shock cools very rapidly. For these core collapse supernovae, the progenitor has lost all of its hydrogen, or most of its hydrogen at least, and is relatively compact. So there's a lot of room to grow and lose heat really quickly. So that's why you have these drops that have the drops happen really quickly within just a few days. But the drops last longer if you're able to look in the UV, and they're also more significant. So in these objects here, there are a couple objects where you don't see any evidence of a shock at all in the optical, but in the UV, there's this one, and then there's an upper limit before the supernova rises, and this one there's an excess at early times. So the UV is really where you want to go to look for these shock breakouts. Some exceptional objects: gamma ray burst 060218 got swift slewing, and so 2 minutes after the gamma ray burst part of the explosion, Swift started observing and saw this very UV bright peak that lasted about a day. The top panel is the X-ray light curve. The bottom panel is the 6 UVOT light curves. So that one was triggered by a gamma ray burst. In 2007, 2008, we were looking at this particular supernova, 2007 UY, and while we were looking at it, another supernova in the same galaxy exploded. Okay, so this is a half hour long, roughly half hour long, no, not even 600 seconds. So within the 30 minutes that we were looking at it, an explosion of duration 5 minutes happened with it. That shouldn't really happen in numbers, but we were very lucky. But you can get even luckier if you design things that allow you to respond really quickly. So here's an example of an object that ZTF observed, where their system of making rapid observations, identifying new transients, and very quickly letting humans know things that were going on, resulted in this observation, where you see this UV bright peak that then fades over a couple of days. And then in the optical bands, there's only basically one data point that's high before it's the radioactively powered part takes over. So this is something that you really have to look at in the UV. And so the UV observations are more constraining. Type 2 supernovae are very hot and blue at early times, but then they fade. And that fading is due to two effects. One is just the temperature. Your temperature is dropping from, well, it's much higher even earlier times, but by the time Swift gets there, it might be 30,000 Kelvin, and then it's dropping down to, 10,000, 8,000 Kelvin over a period of weeks. But you have the black body temperature, as well as changes in ionization, iron 3 becoming iron 2, that also starts blanketing the UV parts of the spectrum. On the left is an early spectrum, and then just a week later, you can see how much more line blanketing in the right panel there is. And then these are models from Luc Dessart, where you can pull out which elements are contributing to that absorption. And then finally, I'd like to mention superluminous supernovae that were only really discovered a decade ago using wide field surveys that could catch things in faint galaxies, because they weren't looking in galaxies for the supernovae. But these are objects that are much more luminous in the UV. So here plotted in black is a type 1a supernova, and then they're scaled to be the same flux at 3000 angstroms. Superluminous supernovae are actually more luminous in the optical than a type 1a supernova, but then their UV flux gets stronger in the UV compared to the optical. So these are going to be very important probes of the high redshift universe, as you think of the ultraviolet light being redshifted into the optical. So here's an example for Gaia 16 APD, just to demonstrate your V-band observations, how they would change. But if we look at it spectroscopically for that object, you can keep redshifting it all the way back to a redshift of 20, or whenever the progenitors that result in these types of explosions, whenever they first formed and died, they're still going to be bright enough for the James Webb Space Telescope to detect those. So back to the very origins of the universe. So that's what really gets me excited about the future. And so that's one of the things that we're doing, is taking all of this photometry, matching it up with spectra so that we can create time series models of the flux versus wavelength versus time that you can then redshift to wherever you want, put in whatever filter system, telescope system you want, and you can predict what you might be able to see, or after you see things, compare directly to the observations at low redshift that we have. So I will just leave you with this final slide that is sort of a graphical summary of my current and future work in using Swift and Hubble to detect the ultraviolet flux from nearby objects that we can then use to understand distant objects where that UV flux is redshifted in the optical, so that we can understand the whole universe using the UV. Thank you.
Thank you, Peter. Is there any question in the room? In the room? Ultraviolet?
Yeah, very nice question. Well, the case where you discovered one supernova that was just 1 year after the other in the same galaxy, right? That which type was it? Type two?
Okay, so he's asking about the types of these supernovae. So they were actually both, I think they were both type 1b supernovae.
So, but can you put any constraint on the expected galactic event rate? I mean, it's something that we saw only once, coming from the same galaxy in 2 years. And if so, if you can put any constraint on the galactic rate.
Okay, so he's asking if we can put any constraints on the galactic rate of supernovae based on seeing multiple supernovae in this one. So for this one, individually, no. Actually, this host galaxy, this is actually like I want to say there have been maybe 5 supernovae discovered in this galaxy within the last 50 years. We call those siblings, supernovae that happen in the same host galaxy. There have been a few other prolific galaxies that have had 5 or 10 supernovae within the era of modern observations. And so those can put, I'm not familiar exactly with how they've compared those with the star formation rate that they've calculated from the galaxy observations itself, but I think that is a useful thing to look at to see, okay, once you've got a large number of galaxies and a large number of supernovae, you can put better constraints on the rate and how that corresponds with the star formation. And that seems like something that LSST with Rubin will give us lots of good constraints. That's a really good idea.
Yeah, so thanks for the talk. Have you looked into more, let's say, queer transients like F-spot or like plus blue transients?
Okay, so Tomas is asking if we've looked into rare transients like the fast blue optical transients and such. Yes, we certainly have. Sometimes in my talks I focus almost more on weirdos than the normal ones. But for example, 2018 cow was one that the UV observations were very important in constraining the total luminosity, because that one was UV bright. And the spectra relatively featureless even in the UV, that it was a very interesting object. But yeah, those ones, especially because of their high UV luminosity, are really interesting. So in terms of the supernova classification and trying to cover all of the types, the weird ones are certainly things that we're interested in. The 1BNs, there was a new one this week that we observed that was at a redshift. One thing I didn't mention is that most of the supernovae we look at are very low redshift. The type 1As in particular, I mean, all of them really a redshift of 0.02 is where most of our swift supernovae are within that. But this 1BN is at a redshift of 0.06, but based on its colors, I expected, hey, if it's really blue like the other ones, we should be able to see it. I requested swift observations. It turns out it's even bluer than 2006 JC that was the previous sort of prototype, and slightly more UV luminous than that object, and we clearly detected it. So yeah, understanding actually this plot. This plot here, the axis on the top right, this redshift limit based on regular swift observations is kind of what I use to look at. Is it reasonable to try to go after this object at this redshift? And especially as we get weirdos, and if we don't know what colors to expect, yeah, we try to observe those and try to understand them better.
And you go back to the previous that you were showing the swift image, so two supernovas and the host galaxy. So I guess in the archive you have produced of this telescope, yeah. So because here I'm not talking about the supernova, but all the background or foreground sources using the UV that have no counterpart. I guess it's optical image of the galaxy. Have you cataloged these kind of sources? Which kind of these local stars in the Milky Way?
Okay, so he's asking about the from these archival images we have, if we've archived or cataloged the data and found counterparts and such. So there is a UVOT serendipitous source catalog. I don't recall how much matching is done with the optical databases. But yeah, we have, I mean, there's when I look at the images for the supernovae, just a wide variety of seeing very blue objects that are probably background quasars. There's lots of background galaxies or background quasars. There's lots of other things in there to be found, and that's, you know, usually when we're observing these, we're all I'm caring about is the brightness of a single source in that image. You know, in this case, another one popped up in that same image. But yeah, there's lots of other data. So just to broaden that, anyone that's interested in UV or X-ray observations, interested in knowing what's already been observed or how I can help you get swift observations that will help with your science, you know, I'm happy to talk about that. I'm here all afternoon. That's something that we'd like to maximize the science with Swift, whether it's from the archive or from new observations that you can propose.
Any other questions in the room?
Any questions on Zoom?
Okay. So he mentioned that he will be in my office in the third floor for the afternoon. I guess we're happy to talk to people if they come, or that you want to chat with Peter at some point. I would like to highlight what you just mentioned, that we, the supernova community, use your help many times triggering observation of supernovae, but I guess you're happy to, if any of you have any interest in getting swift data for your science, I guess you can give them some path to follow or whatever.
Yeah, because
forms and all that, right?
If there's interesting things from ZTF or EPESTO where you guys identify a new supernova, you don't have to go through me or wait for me to wake up or whatever the time zone difference is. I have I even have some blog posts about how to submit. Here's my recommendations for modes, all sorts of things for submitting target of opportunity requests.
That's great. That's great. Thank you very much. So let's thank again, Peter, and let's pizza. Now. Thank you. Bye, Zoomers. The pizza, I guess, is there. I have no idea how this works in the patio, right?